Okay, continuing where we left off after that first video, we're going to move on to more examples, but I just wanted to come back and revisit this picture just for a moment and a couple of things that we noticed. So we found that first example we did, we were closing in on this closed point, and we found when taking a limit, there's no problem there. It's actually just the same as like evaluating a function at a given point. At -2, the limit of f of x as x approaches -2 is the same as the function value. But there were some interesting aspects when we approached a point like this and then a point, like what was happening here. This we're going to refer to as a hole. Okay, there's a point that's just been removed and there's this gap. It's infinitely small little gap. And we saw, hey, when there's a hole, it's actually the same as back over here because we can still look at how it approaches from both sides, and we'll just notice where that is, and it's happening at y equals 2. So that limit was 2. This one, though, gave us more trouble. This we're going to refer to as a jump. So if you think, as you're walking along the function, it jumps up and then continues along. There's this gap, right? And so if you are looking at a regular limit, we call a two-sided limit when you're approaching from both sides. If it's a jump, then we know that that limit does not exist because it has to approach the same y value from the left and the right. But we can take the one-sided limits. We can take the left only or the right only, but we can't do both of them together because they don't equal each other. Okay, so that's a good reflection before we go on to the next set of examples. And here we are. So now we're going to look at some limits, but we're not going to have a graph. When you have a graph, turns out much easier than if you're given, say, the expression for the function. So here, instead of a graph, we're actually given what that function is. Okay, determine the limit. Part A, the limit of 5x squared as x approaches 6. Okay, so let's think about this for a moment. We're actually going to compute the answer. We're not going to do it visually. And so you think, all right, 5x squared. Well, that's a parabola, right? If you picture the graph. Does that parabola, does it have any holes? Are there any missing points? If we just kind of think of that. There's no holes, right? Does it have any jumps? No holes. Are there any jumps there? No, no jumps. It's all this, we'd say it's very nicely smooth, very nicely behaving function. So what does that mean? It's like that first example we did. To find the limit at 6, all we need to do really is plug this in because it's going to be the same as the function value. So I've got a note here. Does f of x equals 5x squared have a hole or a jump? And I mean, you could think anywhere, but even does it have a hole or a jump specifically at that x value in question? You're like, well, no, it doesn't. Actually, it doesn't have any holes or jumps at all, ever. If it doesn't, if not, then we can simply just plug this number in. So 5 times 6 squared. If we compute that, I'm going to grab my scientific calculator here, my TI. 5 times 6 squared gives us 180. And there's our answer. So this one behaves very nicely. If it doesn't have a hole or a jump, we can just plug that in. Turns out there is another case. Vertical asymptotes also give us problems. But we'll encounter those soon enough with limits. For now, just think holes and jumps. Are there any holes or jumps? If no, we can plug in. Okay. Well, moving on. Let's take a look at this. Determine this limit. Getting a little bit more complicated. The limit of x squared minus x minus 6 all over x minus 3 as x approaches 0. You think, okay, okay. I have no idea what this looks like. And I don't have to know what it looks like is really nice. Um, and you might think, does it have holes or jumps? I don't know. Now I'm dividing by x minus 3. And so there is going to be something kind of funny going on. But specifically, right back here, is there a hole or a jump at the x value in question? Is there a problem at 0? X equals 0. And we can find out pretty quickly if we just go ahead and plug in 0 if there's an issue. So if I plug the 0 in, 0 squared minus 0 minus 6 over 0 minus 3, well, isn't that just going to be negative 6 over negative 3? And I do get a number, and that's going to be my answer. So it turns out there is going to be a problem, but that problem is not at 0. So if I'm talking about the limit as x approaches 0, I can do it the same way as this last problem. I can just plug it in, get an answer, and I'm set. Okay, so if there is a problem with this function, it's just not at 0, then where is it? And maybe some of you guys know already. Where is the problem with this function? Well, it's at 3, because at 3 I divide by 0, right? Okay, let's look at that. You know we can't resist. We got to look at it. The next example, part C, and you can tell I'm getting sloppier with my notation. The limit, same function, x squared minus x minus 6, all over x minus 3. And now this time, all we had to do it, we're going to take the limit as x approaches 3. Okay, so clearly we're not just going to be able to plug this in, because if we plug in 3, we're dividing by 0. Actually, there's more to the story. I'm going to write it down here. Go ahead and plug 3 in to all of the x's. All right, 3 squared minus 3 minus 6 over 3 minus 3. Sure, the denominator is 0. Look at the numerator. What happens to the numerator when you plug in 3? 9 minus 3 minus 6. Don't you get a 0 there as well? Okay, that is key. So zeros in the denominator, they're a hint that something's wrong. But when there's a 0 in the numerator, that tells us even more. 0 over 0. So I don't know if you learned this back in pre-calc. It might have depended on your teacher or maybe your book. But I'll tell you now. Okay, so we just discovered this. Plugging in x equals 3 gives 0 over 0. 0 over 0 means there's a hole at x equals 3. Okay. Specifically 0 over, if it was some other number over 0, that'd be a different story. And we'll talk about that situation later. But if it's 0 over 0, then that means there's a hole. So what is that? Okay, so if there's a hole, think back to the last problem with the graph. If there's a hole, there is an answer to this limit. It's just not as obvious. We can't just plug the 3 in order to realize that answer, but there is an answer. So what are we going to do? And different problems, you approach them slightly differently. Basically, what we want to do here is simplify. If we can simplify this, if there's a way to write this simpler, then maybe then we can figure it out. And maybe you guys even noticed this already. Okay, well, and here's kind of that's what I just said in words. Simplify, and by try again, I mean try to plug x equals 3 in after it's simplified. Okay, let me pull this up here so we can really focus here. What does simplify look like? Well, maybe the numerator can be factored. And it turns out it can. And I'm just going to show you guys the whole problem from here. That numerator, if you factor x minus 3 times x plus 2, and of course it's over x minus 3. Hey, what do you know? X minus 3's cancel out. And so let's look at the simplified version. We're still going to write the limit right? The limit as x approaches 3, the limit as x approaches 3. But now we'll just think about it as x plus 2. Hey, can we plug in the 3 now? Sure can. Plugging in the 3, we do get an answer this time of 5. And that's pretty nice. So what's kind of cool is, right, we know there's a hole, but how do we actually find out where that hole occurs? It's because we were able to factor, and when we canceled, what that did to the graph, this is, it's surprising. Canceling those x minus 3s filled in the hole. What do I mean? The graph of the original function, this guy back here, that's the same as the graph of x plus 2. This graph and this graph are identical, except this one has a hole at x equals 3, and this one doesn't. Otherwise, they are exactly the same. Because that can be simplified, but when you simplify, you fill in the hole. The graphs are not perfectly identical, but they're very, very close. Just at x equals 3 is there a difference. So what is that? I mean, that's just a line, right? I mean, if you were to graph that, x plus 2, it's got a, just a quick y equals x plus 2. Goes through 2 there. So 3 would be out here someplace. So what's going on? That first function, this guy, has a hole, and it occurs up here at 5. It's like, oh, I can't plug it in. But when we do all our work and we cancel it, we fill in that hole, and then we plug it in, and boom, we got our answer, 5. And so we know we did it correctly. The simplifying just helped us get around the fact that we didn't have a graph to look at. Pretty cool, pretty nifty. Okay. Let's keep going. I've got another one in the same vein. How about this? The limit of x squared minus 16 over x plus 4, and we're going to say x approaches negative 4. So you think, oh, hey, can I just plug in? Like, oh no, 16 minus 16, negative 4 plus 4, that'd give me 0 over 0. There's a hole. Okay, so as soon as we realize 0 over 0, we're going to think, all right, maybe we can simplify. And actually here the factoring is maybe even more obvious. We've got a difference of squares up on the top. And again, I'm going to copy my limit notation. Limit and x arrow negative 4. I'll just factor here. Of course, we can cancel that. And so that brings us just to the x minus 4, limit as x approaches negative 4. Plug it right in, and hey, we got an answer of negative 8. So it works in a very similar way. Okay. Let's do one more before we end this video. Now this is an interesting one, but there is going to be a similarity to the last couple of problems with the factoring. The limit as x approaches 3, and we've got this big fraction, the square root of x plus 1, and then minus 2 on the side there, not in the square root, divided by x minus 3. And again, x is approaching 3. Get rid of this. Like, oh man, these are getting kind of ugly. Well, that's okay. If I can plug in 3 and get an answer, then I'll be in good shape. What happens when we plug in 3? Right? If it works, then we're done. Oh no. So that's going to be the square root of 4, 2 minus 2 over 3 minus 3, and oh, we got 0 over 0 again. What do you know? Okay, well, there's obviously a hole again. But where in the last two problems we were able to pretty quickly factor and cancel out the denominator, well, that's not the situation here. There's a different technique. And maybe you guys are keyed onto it from the algebra review, or I think it was in the algebra review portion of the review, or maybe even from the calculus preview. There was a question about a square root, and the hint was to multiply by the conjugate of the numerator. I don't know if you remember that one. So you might be watching this video and thinking, I know what to do. Maybe, I don't know. I'm going to tell you anyway. Here's how we're going to simplify this. We're not going to do it by factoring. We're going to think, hey, that numerator, let's multiply the top and the bottom by its conjugate. So the conjugate meaning it's going to be identical to the numerator, except the minus sign turns into a plus. So I'll multiply the top and bottom by the square root of x plus 1 plus 2, and well, the denominator needs to be multiplied by the same thing. Okay. So what happens there? How is this beneficial? So we're going to go ahead and FOIL the numerator. Let me show you what this is going to look like here. So square root x plus 1 times square root x plus 1 is just x plus 1. The square root and the square root would be squared, so that would cancel. Also, because it's a conjugate, right, I multiply the square root by positive 2. Then I multiply the same square root by negative 2. Those middle terms would cancel. And finally, negative 2 times positive 2 gives me the minus 4. So the whole reasoning behind the conjugate is so that when I do those middle terms, they cancel out. And I no longer have a square root because those first two terms when they multiply. And then we got the minus 4 also. Okay, so there's my numerator after multiplying by the conjugate. How about the denominator? Okay, here's what's going to happen with the denominator. Don't FOIL. We do FOIL the numerator. Don't FOIL the denominator. Simply write it as, keep it factored, x minus 3 times square root x plus 1 plus 2. Don't FOIL the denominator. Why? Why don't you want to multiply that out? Because we really want this x minus 3 to cancel. Right? That's what we did before. If we can cancel that out, then we're set. And we can plug in the 3 and not divide by 0. Are we going to be able to get that to cancel? Yeah, because look at this numerator. Isn't that, when we simplify, isn't this x minus 3? X plus 1 minus 4? So we can cancel the x minus 3's. So that cancels out the entire numerator, and all we're left with is this. Slide on up here. Once that's gone, it's 1 over the square root of x plus 1 plus 2. And think, oh, that's awesome. I canceled out that x minus 3. Now I can plug the 3 in. Right? So I'll show you all my work. 1 over the square root of 3 plus 1 plus 2. Well, that's 1 over 2 plus 2. My answer, our answer, is 1 over 4. We got an answer. We knew there was an answer because it was a hole, but it took some algebra work to put us in a position where we could plug that number in. So the theme, what's similar, if you have a hole, if you try to plug in, basically try to just plug the number in to get the limit. But if it results in 0 over 0, then you know you're going to have some algebra to do. Maybe as simple as factoring. Maybe it's something with a conjugate. And I'm not saying those are the only possibilities. There might be other things you could do, finding common denominators of stuff. Fractions inside of fractions can happen as well. But in the end, the goal is to cancel out that troublesome part of your denominator, and then you can plug right on in. Okay, let's stop this video here. We've gone over 20 minutes. That's all right. I'm glad we fit in this last example. We will pick up and do some more in the next one.